Great. So thank you for that introduction. So what I'm going to talk about today over the next 45 minutes or so is this scattering models for simulation and design of quantum hardware. And all the results that I'll show you are basically, they fall under this larger umbrella of quantum technologies. The motivation for a lot of these quantum technologies really stems from the fact that, in experiment and in experimental applied physics, there has been a recent and there have been many recent developments that have allowed us to control quantum systems at individual levels. So we can control individual quantum systems, and consequently, there has been a drive towards building quantum hardware that can solve technological problems. So for example, you have quantum computing, where you're trying to use these controllable quantum systems in order to solve computational problems faster than you would do on a classical computer. You also have things like quantum communication, where you're trying to use quantum states in order to communicate over long distances, communicate both classical and quantum information over long distances. And you have quantum metrology, where you're trying to use quantum states in order to measure and sense very, very small and quantities very accurately. So all of these quantum technologies have really motivated us to figure out ways in which we can understand the basic building blocks of quantum hardware, simulate them, and scalably design them. And so from a hardware simulation perspective, so if you want to understand how these devices work, this has raised a few key questions, some of which I'm going to address in my defense. So the first question that this has raised is that, what are the mathematical models that you can use in order to understand physical devices that we are using to build quantum hardware? And this question, of course, has existed for a fairly long time. It is not really a new question, but I'll still go over a very qualitative answer to this question at the beginning of my talk. More importantly, once you do have these mathematical models, then, the question that you could ask is that what kind of numerical or analytical techniques can I use to simulate these models? And this is an even more important question when we think about quantum systems, because we know that simulating quantum systems is usually a difficult problem to solve on classical computers. So we really need to be careful about what exactly is it that we are trying to calculate, and how are we going to exploit some structure in a problem in order to do that calculation. And finally, can we use these models in order to solve practical design problems in quantum hardware? And so this is something that I'll touch upon in the second half of my talk, where I'll be showing you examples of experimental systems that we can understand using these mathematical scattering models, as well as how we can go ahead and design these experimental systems for concrete quantum technology applications. So in order to understand the general framework of quantum hardware and develop some general model that we can fit different applications in, it is actually very instructive to draw a parallel between quantum hardware and classical hardware. So all of the people who have been studying electrical engineering would probably find this very trivial, but if you think about a piece of classical information processing system like a digital circuit, you can think of it as comprising of two blocks. So you have some kind of classical information that is usually your bits of information that are encoded as voltages or currents. So that's the physical system that we are using in order to represent our information. And then you have these information processing systems, which are essentially these gates that take as input these voltages and currents and perform some computation by the virtue of their own physics on your classical information. And by connecting many of these gates with something as simple as wires, you can construct pretty complicated systems which can perform complicated classical information processing tasks. So when we think of quantum hardware, we really have a very, very similar system at hand. So we have now, instead of classical information, quantum information that is stored in the state of quantum systems, which we call qubits. And these states can be manipulated locally by applying some kind of controls to the qubit. So you can perform single qubit operation by simply locally manipulating the qubit. But at the same time, you can connect these qubits to what I call quantum wire, so that you can get these qubits to interact with each other and perform global operations on all of these qubits taken together, and thus build more complicated quantum information processing or quantum technology hardware. So the precise physical implementation of these qubits. So what is the system that I use for a qubit? What is the system that I would use for a quantum wire? And how exactly do I apply this local control really depends on what application you're addressing. So you have a plethora of physical systems that you can choose for these quantum hardware. And depending on your application, one physical system might be better to use than the other. But just to give you an overview of the different kinds of physical systems that we can look at in quantum hardware. So if you think about qubits, the qubits are usually implemented with what are called localized physical systems, right? And these localized physical systems are essentially physical systems that confine electrons or photons or confine particles of some sort into small spatial volumes. And so you have examples of localized physical systems, just quantum dots, or you have atomic systems, which are confining electrons in a small physical volume because of Coulombic potential. Or you have superconducting qubits, or more recently, people are looking at color centers and solid state systems. So you have all of these different physical systems that can act as qubits in different contexts. But when we are thinking about that from a hardware perspective, we want to abstract away all of the physics of these systems and consider a simpler model that we can think of. So if we have a localized physical system, the usual model that we can think of is a system that has a finite or accountably infinite number of energy levels. And the quantum information is then stored as a superposition of these finite or countably infinite number of energy levels. So the second component of quantum hardware that's also very important are these quantum wires. And these quantum wires, as I said, essentially connect multiple qubits together or allow you to take input and feed, give input or feed, take output from these localized physical systems. And these wires, quantum wires, are actually not different from classical wires. So you have structures like dielectric waveguides, transmission lines, or more complicated three-dimensional nanophotonic structures. So you can use these structures for connecting different qubits and getting them to interact with each other. But again, from a quantum hardware perspective, while all of these different implementations of a quantum wire can have very different physics, they can be thought of as, again, a system that supports a continuum of energies. So unlike localized physical systems where you could only have some discrete energy levels, when you think of these quantum wires, you can have a continuum of energy levels. And so you can construct wave packets that can propagate in this quantum wire and communicate in between different qubits. So then what we really want to study is how this localized physical system interacts with this quantum wire. So this is a coupled system that we'll be looking at for most of my talk. And as I'll show you when we come to the experimental part of my talk, that a number of physical systems that are interesting in quantum technologies can be fit into the same format, and the same theoretical tools can be used to analyze the physics of a large number of these systems. So I'm going to divide up my talk into three parts. So the first part, I'm going to focus more on some theoretical results on how, on calculating what are called scattering matrices, which I'm going to define in a minute. For this coupled system. So the second part of my talk, I'm going to use these theoretical results in order to analyze some concrete experimental systems that we can implement in a variety of physical platforms that could be useful for quantum technology applications like non-classical light generation and storage. And in the third part of my talk, I'm going to then show you how we can use these simulation models in order to design or solve concrete design problems in the space of quantum technology. So without further ado, let me get started with the first part of my talk, which is the scattering theory of these open systems. So as I mentioned, what we are essentially interested in doing is understanding the interaction of this localized physical system and this high dimensional bath. And while this problem in the most general interaction that we can think of is pretty complicated to simulate. So what we want to do in order to get some tractable theoretical result is to make some assumptions on how this interaction happens. So the most common assumption that is made in understanding the interaction of these two systems is what is called the Markovian assumption. So we get what is called a Markovian model here. And physically speaking, the Markovian assumption essentially says that the localized physical system interacts with all the energies in the bath. So the bath, if you remember, supports a continuum of energies. So the localized physical system interacts with all the energies of the bath equally. So it's a completely broadband interaction that we are looking at. And this as a consequence of this broadband interaction, what you can show is that if you just look at the dynamics of the localized physical system, if you effectively remove using some mathematical procedures, the dynamics of this bath, then what you get is dynamics which only depend on the current state of your localized physical system and not on the history. So you get what is Markovian dynamics, which is why we call these systems Markovian. A natural generalization of these systems are non-Markovian systems, where you account for frequency-dependent interaction between the localized physical systems and the bath. And this frequency-dependent interaction makes this problem of understanding the scattering theory of these non-Markovian systems a lot more complicated. But we have some results on specific class of non-Markovian systems that we can tractably simulate. And then we can actually go ahead and generalize both of these results and think about systems where my localized system is interacting, instead of interacting with a one-dimensional bath, which is what we typically assume that a bath can be modeled with a 1D wave equation, we think about baths that can be modeled with full three-dimensional inhomogeneous wave equation. And the motivation here really is that practical devices are actually described by three-dimensional wave equations and not by one-dimensional wave equations. One-dimensional wave equations are suitable approximations to understanding these devices in a number of cases, but there are a number of quantum hardware that exploit structures that cannot be described with one-dimensional wave equation, and then we have to think about how we will model this physics of three-dimensional wave equation in our system. So before going into these results, it might be worthwhile for me to give you a very qualitative description of what is it that we want to calculate. So, and what has already been done in generally speaking in this area. So what has already been done is that if you're interested in just looking at the state of the localized physical system, so if you're not really interested in the dynamics of the bath, then what you could do is that you could kind of derive these effective equations of motion for the state of the physical system, which is obtained by tracing away the state of the bath from the complete state of the system. And this gives us what is called, the master equation framework for understanding these models. And this has existed for a very long time. So there has been a lot of work in developing master equation models for different classes of quantum systems interacting with one-dimensional, three-dimensional bath, as well as excited by lasers or non-classical states of the bath. And so there is a huge amount of literature that really exists on this. But one of the things that is very difficult to do with these master equation framework is that we cannot really understand or calculate easily what the state of the bath is. So while we provide you with a very good description of how the state of the localized system behaves, we are not really able to capture in a tractable fashion the state of the bath. So, and the state of the bath is of importance in a number of applications, such as quantum communication, metrology, or even optical quantum computing, where the state of the bath is the essential quantum resource that you want to use in these applications. So there, it is of interest to compute the state of the bath tractably. And one important point that can be made here is that we really want to compute not just the entire state of the bath, which can be a pretty complicated object, but the projection of the state of the bath on some few photon spaces. So we have, the full state of the bath lies in this very large Hilbert space, but what we really want to do is project the state of the bath on the smaller Hilbert space, some subspace of this Hilbert space that actually has what is of interest to us from a quantum technology standpoint. So we want to be able to use the fact that we want to make this projection efficiently in our calculation. So this framework is what I think of as a scattering theory framework, because you're thinking of this localized system as being excited by some incident state, and it is scattering away into this output state that you're interested in calculating. Okay, so so now let me start with describing the results for the three classes of models that I described. So if you look at these time-dependent Markovian models, so as I mentioned, these Markovian models are models in which the coupling between the localized physical system and the bath are completely broadband. Are completely broadband in nature. So if you write it mathematically, for those of you who are familiar with a little bit of quantum mechanics and open quantum system theory, it is you're writing your interaction Hamiltonian. And in the interaction Hamiltonian, you introduce a coupling operator L, which is coupling to the annihilation operator at frequency omega for the bath. And this L is independent of omega, and that's what really your Markovian approximation is telling you here. And this Markovian approximation is a very, very good approximation for most of the devices that people look at in quantum hardware. So you have waveguide QED devices or devices coupled to phase space, or even more complicated three-dimensional structures. You can often describe them within this Markovian approximation. And so the scattering theory of Markovian models also had been extensively studied when we started thinking about this problem. However, one of the things that was actually not really captured in most of the calculations that appeared before we started working on this was the fact that the system was often assumed to be time independent. So you used to have a system that did not have a Hamiltonian that is changing with time. In concrete quantum technology applications, you're often changing the system of the Hamiltonian of your system as a function of time by applying some pulses in order to perform some information processing task. So what we really were interested in doing is characterizing the output state of the system, so characterizing the state of the bath when your Hamiltonian was changing as a function of time, and not just when it was time independent. And naturally, with this framework, we could also capture systems which were time independent, so it was a more general result in this class of problems. And so the essential result that we came up with, and this is work that I did in close collaboration with Kevin Fisher, who used to be a PhD student in Yelena's group a few years back. And so the essential result, very intuitively, that we came up with was that if you want to understand the scattering of photons from this coupled system here, which is a complicated large Hilbert space, what you could do instead, if you assume the Markovian approximation, is understand the dynamics of this localized system, but with a slightly different Hamiltonian. So you could effectively remove the bath from your calculation and just think about this localized system with an effective Hamiltonian that depends on both the Hamiltonian of the system as a function of time and the coupling operator between the system and the bath. So if you could compute the propagator of this particular effective Hamiltonian, you could in fact compute the propagator for this first system completely. So that is the essential result that we had here. And because these localized systems were usually small systems that we could extractably solve numerically or analytically, this really allowed us to study the state of the bath in a tractable fashion. So of course, the next step that we wanted to take was to generalize our results to these non-Markovian models where the coupling operator L becomes frequency dependent. And while this obviously captures the cases where this coupling operator is frequency independent as well, this has become of interest more recently because there have been physical systems that people have constructed in experimental settings where you can't really approximate them with these Markovian models. So these include these giant atoms in superconducting qubits that have displayed potential to perform quantum information processing tasks that are more complex than you can perform with Markovian systems or these time delay feedback systems that we looked at recently, and I also talk about them at some point in my talk. So all of these systems are systems that you can't really describe accurately with Markovian approximation, and you really have to account for non-Markovian dynamics that's happening here. Now, the problem with non-Markovian dynamics is that, again, generally solving for a non-Markovian system is almost intractable. So we again need to make some assumptions on how the non-Markovian system behaves, or what some assumptions on the form of interaction between the localized system and the bath. So what we did really was to consider just a specific class of localized systems, which are called these bosonizable localized systems. And these systems are, although they feel to be a bit restrictive, they can still capture a very, very large number of quantum systems that we are interested in looking at. And the idea behind these bosonizable system was that I can think about the Hilbert space of my localized system, which had some discrete energy levels, and I can think of the Hilbert space of this localized system as a collection of bosonic modes. So if you're thinking about, for example, a two-level atom, which has two states, a ground state and excited state, you could essentially think about one boson, or one bosonic mode in which you can put bosonic particles. So you could say that I can think of two-level atom as one boson mode with the ground state of the two-level atom mapping to the vacuum state of the bosonic mode when I don't have any particles, the excited state of the two-level atom mapping to the single particle state of the bosonic mode. And then, because I only want to restrict my system to two levels and not really consider any other levels that I can add on top of that, I could add repulsion terms in my Hamiltonian for the localized system that would forbid more particles from occupying the boson. So I don't have, I can make it energetically unfavorable for putting more particles in the boson, more particles than one. So then you effectively have description of this two-level atom as a bosonic mode. So as another example, if you take a V-level atom, which is two excited states and one ground state, so again, this is a very commonly occurring quantum systems in a number of applications, then you can think of this as two bosonic modes, right? So one bosonic mode corresponding, so to speak, to each transition in this V-level atom. And you can then map the different occupation numbers of this bosonic modes to the different states of the two-level atom. So the ground state of this two-level atom could then be mapped to the state where where there are no particles in either of the bosonic mode. The single excited state of the two-level atom could be mapped to the case where I have one particle in the first bosonic mode and nothing in the second bosonic mode. And this, the second excited state could be mapped to the state where I have one particle in the second bosonic mode and no particle in the first bosonic mode. And then I could put repulsion terms in order to make it energetically unfavorable in order to put more particles in my bosonic mode and restrict my Hilbert space to just 3 levels. So with these examples, I might have convince you that, you know, even if you restrict yourself to these systems that can be described as boson, by playing with the repulsion terms that you can add to the bosonic Hilbert space, you can actually encompass a pretty large variety of localized systems. And then in these classes of localized systems, the essential result that we had here was that if we wanted to understand this scattering from these localized systems, so even if you put in a few particle incident state, which was not just a single photon state, but maybe a 2 or 3 photon state, then you can compute the scattering matrix of the system by just computing the single photon scattering matrix for the system. So all that you need to understand is how a single particle scatters through this bosonic system, and from this single photon, single particle scattering matrix, you could in fact construct all the higher particle scattering matrix in an analytical fashion. So that was the main result that we had here. Again, I'm not going through any concrete details of how these results come about. They're all there in the reference that is cited below. So if you're interested in the actual rigorous detail, I would encourage you to look at that reference whenever you have time. So this is how we kind of solve the problem of understanding a pretty large class of non-Markovian models. And then finally, going on to the third class of models that we were interested in understanding were these 3D bath models, where we were saying that, oh, you can't really describe these baths by one-dimensional wave equation, but in general, you're describing them with these inhomogeneous 3-dimensional wave equations. So for example, you could have a bath which is described by a 3D scalar wave equation, and then you have a localized system coupling to this bath. What we were able to do in order to solve this, what seems to be a more complicated problem, was actually reduce the solution problem to a solution of 2 more tractable problems. So if you wanted to understand few particles from these 3-dimensional baths, then all that we could do is first solve a classical problem where I forget about the quantum mechanics of the bath and just solve the classical wave equation under excitation from a classical field that is exciting the bath. And I solve an effective 1D problem that depends on the Green's function, or that depends on the bath, on the permittivity distribution of my inhomogeneous bath. So by solving these 2 different models, one is an effective 1D model that I've already discussed how to solve, and this classical wave equation model that people have been solving for decades, we could combine them and solve the scattering problem for a localized physical system that is coupled to this inhomogeneous bosonic bath. So that brings me to the end of my first part of my talk, where I very briefly told you the 3 different theoretical results that we have. And these are the references that you can look at for detailed derivation of these results and proofs and so on. So let me now go on to the second part of my talk, which hopefully is going to be a little bit more interesting than the first part for many of the audiences to understand concrete physical systems using these scattering theory models. So most of the physical systems that I will talk about are interesting as in their own right. So just understanding the experimental, understanding these systems as experimental systems is interesting, but they also have some technological appeal to them. We essentially want to look at physical systems that can be used for non-classical light generation and storage. So non-classical light generation here is essentially this, you can think of as a system which acts like a source of non-classical light. And the idea is that you send in a laser, which is a classical light source, and this source essentially performs performs an operation, a scattering operation on the laser, and gives you a quantum light source that you can use for quantum communication or metrology applications, right? So there are different kinds of physical systems that are used for these non-classical light sources. What we are going to focus on in these talks are things like driven two-level systems, cavity QED systems, or modulated quantum systems. And then we also are interested not only in generating these non-classical light sources, but also in storing these non-classical light pulses. So you not only want a source, but in many applications, you also want a memory for these non-classical pulses. So you want to store quantum information that is propagating in these non-classical light pulses into long-lived state of some physical system. And so there I'm going to talk about these non-Markovian waveguide QED system and bound states that can exist in them, that we can use for implementing these quantum memory applications. Okay, so let me start with perhaps the simplest system that we are going to be talking about, which are these two-level systems. And even though they're very simple, their physics can be quite deceiving if you start looking at it carefully. So the two-level systems are most popularly a very, very simple source of single photons. So the idea here is that you have two levels. You have an excited state and ground state. You drive it with a laser pulse that takes the emitter from its ground state to excited state, and then the emitter decays from its excited state to the ground state to emit a single photon. And so you can use this by choosing your laser pulse properly. You can use this as a source of single photons, of on-demand single photons. You can generate the single photons whenever you would like by appropriately gating your laser pulse. And depending on this laser pulse, you can, in fact, prepare your output state in the short pulse regime. If your laser pulse is much shorter in time domain compared to the time scale at which the localized system decays, you could prepare your output state as a superposition of either having no photons or single photons. And you can control the coefficients of the superposition by controlling the amplitude of the laser pulse. So if you keep your laser pulse short, but keep on increasing the amplitude of the laser pulse, then the probability of emitting a single photon oscillates from 0 to 1, and you can then choose where you want it to be for depending on the state that you want to prepare. Now, what we wanted to do, of course, was to understand the system more carefully and understand the system beyond the short pulse regime. So this is again work that I did with Kevin. And one of the things that we wanted to do was to consider if instead of having a short pulse, if I excite my two-level atom with a much longer pulse or comparable to the time scale at which the two-level atom was emitting, then can I characterize the photon state that is coming out? So, and that we could do very easily with scattering theory. We could in fact characterize the photons that were coming out as a function of space as well as time. So as time evolves, we could calculate what is the photon that's coming out as a function of space. More interestingly, what we discovered was that you could actually use this two-level atom not only as a source of single photons, but also as a source of two photons or two or more photons based on the laser pulse. So in fact, if you were applying the laser pulse for a time for not necessarily in the short pulse regime, but in a regime where it was comparable to the time scale of the system, and even in the short pulse regime. And if you were choosing the laser amplitude to be such that the single photon emission is 0, what we could calculate was that you would actually have significant two-photon emission. And this two-photon emission could be used for a number of quantum applications as well. So a simple two-level atom could not only be used as a single photon source, but also as a few photon source. And I'll show you some results towards the end of my talk, where we will talk about how we can engineer the spectral content of this two-photon source as well. So, but going on to thinking about non-classical light sources, so one of the problems that these non-classical light sources based on, for instance, the two-level atom have is that they couple very weakly to these baths, and you really need to enhance its coupling to the bath using some engineering tricks in order to get a high fidelity photon source. And one of the ways in which this is done in practice is by using this cavity QED setup. And so the idea there is that if you can take your electromagnetic field, or you take the fields that propagate inside your bath, and you confine them into very small volumes using two mirrors, then you could, in fact, increase the local electric field that the two-level atom is coupling to, and therefore increase the effective coupling between the two-level atom and the bath modes. So this coupling, and then you could imagine using this coupled cavity QED system where you have a two-level atom coupling to a cavity mode as a non-classical source of light. So one of the phenomena that happens in this cavity QED system, which is highly relevant if when we are thinking about non-classical sources of light, is this phenomena of photon blockade, where you send in 2 photons and what you get out is a single photon. So you are in fact able to filter out one of the photons, reflect one of the photons, and only produce a single photon source. And the physics behind this photon blockade is actually quite simple. You can understand it very easily by looking at the eigenstates of this coupled cavity QED system. So if you take the Hamiltonian of this cavity QED system and calculate its eigenstates and calculate the energy levels, the eigenvalues of this Hamiltonian, what you find is that if you look, you have, of course, one ground state that doesn't have any photons in the system. And then you have the single excitation states, which have 1 photon in the system. And you have 2 single excitation states, which are split by an amount that depends on the light matter interaction strength G. So the coupling strength between the 2-level atom and the cavity mode. And then you have these 2 photon state, which are split by an amount that is different from the single photon state. So what you do is you create this anharmonicity in your ladder of states. So that means that, that the ladder of states is not really equally spaced. And what this allows us to do is that if we choose a frequency of our single photons that is resonant with this energy, with the single excitation energy level, then the second photon is actually not going to be resonant with any of these excited states. And if it's not going to be resonant with any of these excited states, then it's not going to transmit through. So you can take 2 photons and effectively just pass a single photon through your cavity QED system, and therefore use it as a single photon source. And clearly, you can see from this that this photon blockade should improve as I increase G, because as I increase G, I'm making this spacing more and more non-uniform. And so, however, increasing G in practice is difficult because I need to really engineer extremely small mode volume and high quality factor cavities. So it is technologically difficult to increase G. So one of the proposals that a number of people in the field had was to say that, well, if we can't really make our cavities better, can we just increase the number of emitters inside my cavity in order to increase the amount of light matter interaction? So can we use a multi-emitter cavity QED system instead of a single emitter cavity QED system in order to understand or look at photon blockade? And so we started thinking about how to understand this multi-emitter cavity QED system, and it's actually very easy to do within the scattering theory framework. So you can consider a system in which you have a cavity coupled to multiple emitters, and you can then consider, it coupling to an input and output bath that you're using to excite this cavity QED system, and then taking an output from this cavity QED system. And we were interested in understanding how 2 photons transport through this system. So we had an incident 2-photon state, and then which was a continuous wave state. So it was 2 photons at the same frequency. And then we would characterize using our scattering theory what is the 2-photon state that is coming out, transmitting through this cavity QED system. And this 2-photon state can be calculated very easily by applying the scattering matrix of this cavity QED system on the incident state, which are simply plane waves at frequency of the laser. And so while you could calculate this 2-photon state, which is described, of course, by a function of 2 variables, which are the positions of the 2 photons, what is of interest in experiments is this photon coincidence count, which really is the value of this 2-photon state evaluated at the same position. So what you're interested in saying here, or the question that you're asking here is, are the 2 photons transmitted at the same time, or are they transmitted with a delay? And if you properly normalize this quantity, which are details I'm not really going through it, what you would find is that if your G2 is much smaller than 1, then that would mean that not the 2 photons are not transmitted at the same time, which would essentially say that the presence of 1 photon forbids the transmission of the second photon, and which is what we would intuitively expect out of a situation which has photon blockade. So the extent of photon blockade can in fact be measured by this equal time 2-photon correlation function and how small its value is. So then we went on to study this equal time 2-photon correlation function. And what we found surprisingly was that as we increase the number of emitters, quite unlike what we had expected, the photon blockade actually becomes worse and worse. So increasing the number of emitters was not actually improving this photon blockade. So it was not really enhancing light matter interaction in the context of this photon blockade. And while this might seem counterintuitive at first, we could actually explain them very easily by thinking of this multi-emitter system in a slightly different way. So you have a multi-emitter system which has n identical emitters that are coupled to the cavity mode, or you could effectively think of this multi-emitter system system as one large spin and half emitter coupling to the cavity mode. So you can combine these n emitters into one big emitter, but with n energy levels. And then you could see that as you increase the number of energy levels of your spin and half systems, as you increase the number of emitters, then this was essentially tending towards something that's completely harmonic in nature. It was tending towards the energy level structure of a harmonic oscillator. And then you were essentially left with two coupled harmonic oscillators, which would be a completely harmonic system, and therefore you would not see any photon blockade through the system. So that explains, why you can't use these multi-emitter systems for producing this photon blockade. But what we discovered interestingly was that if we consider a system in which the resonant frequencies of the emitters and the cavity don't align with each other, then the photon blockade would improve with the number of emitters. So as you increase the emitters, even though you're tending to a system in which you have essentially two harmonic oscillators coupling to each other, you could find a frequency where you could still see photon blockade. So this was a slightly counterintuitive effect that we discovered. And we could explain this by looking more carefully at the two-photon wave function and thinking about how the two-photon wave function scales with the number of emitters. So one convenient way of doing this was to say that I can write my two-photon wave function as a sum of two contribution, which we could actually very rigorously define using scattering theory. So the details are again in the reference down below. But one term would be a harmonic contribution, which would correspond to a system that's completely harmonic. So if we ignore the anharmonicity introduced by the emitter, we would have a completely harmonic wave function. And then you have a two-photon, and then you have a contribution which captures the effect of anharmonicity on the two-photon scattering process. And we could study how these different contributions scale with the number of emitters in our system. So for a resonant system, what we found was that the harmonic contribution actually did not really scale with the number of emitters, so it was pretty much constant. But the anharmonic contribution scaled inversely with the number of emitters. And this really told us that, as you increase the number of emitters, then the system was becoming increasingly harmonic because the anharmonicity was becoming smaller and smaller. But if you look at these detuned systems, what we found was that if you choose a frequency properly, then both the harmonic and anharmonic contribution was scaling inversely with the number of emitters. And what this means is that your system is not really becoming harmonic in the limit of n tending to infinity, and it's going to remain relatively anharmonic in this limit, and therefore you can expect photon blockade even when you are effectively seeing two harmonic oscillators coupled to each other. And of course, this had consequences on the, because the harmonic and anharmonic contribution were both scaling with 1 by n, it would mean that the transmission through the system was becoming smaller and smaller. So there was a trade-off between how good your photon blockade could be and how highly this system can transmit photons through it. So this is where I would like to end the story of this multi-emitter cavity QED system, and maybe look at, within the same framework of non-classical light sources, slightly different design problem that we might be interested in. So, and the problem is that can we engineer the spectral content of these photon wave packets? So with these two-level systems and multi-emitter system that I talked about, you could produce these photon wave packets. You could produce single photon wave packets, for instance, but can we engineer its spectral distribution is another important question that might have practical implications in a number of technological applications. And so the idea here is that, if you just think of the system that we have been talking about for up to now, where the Hamiltonian of the system is constant. So you're talking about like a two-level system or a multi-emitter cavity QED system. The Hamiltonian of the system was not really changing with time. And consequently, the output photons, the spectral content of the output photons is only determined by the spectral content of the input photons. And while you could engineer that to some extent, it doesn't give you as much of a control over the spectral content of the output photon as you would like in a number of applications. However, we could imagine making the system time dependent by applying a modulating signal on this. So we could take a Hamiltonian, which is a function of time. For example, you could be taking a two-level atom and you could be changing the resonant frequency of the two-level atom as a function of time, and that would allow you to change the spectral content of the output photon. So we were interested in studying these modulated quantum systems as well, and we thought about how single and two-photon scattering looks like for these modulated quantum systems. So if you think about single photon scattering, for instance, if you're applying a periodic modulation on these localized quantum systems, then a single photon at a particular frequency would in fact scatter into a single photons with frequencies that are displaced by the modulation frequency. And this is, a very obvious result of the fact that your Hamiltonian is periodic. So your output state can have changes in frequency that are governed by the periodicity of your Hamiltonian. And you could control the relative contribution of these different frequencies by engineering the periodicity of your Hamiltonian. If you look at two-photon scattering, a very, very similar result occurs, where if you take a two-photon wave packet that exists as a function of two frequencies now, then when you scatter it across this periodically modulated Hamiltonian, then this two-photon wave packet is actually going to be replicated in this 2D, in this omega-1, omega-2 space on a lattice whose periodicity is determined by the modulation frequency of your Hamiltonian. So, and then you can again control the relative contribution of these different lattice points by controlling the modulation that you're applying on the Hamiltonian. So the reference that I have below here actually has a lot of results on how we can relate, for those of you who are interested, the different sidebands to the Floquet decomposition of the Hamiltonian, and there is a discussion of the analytic and geometric properties of the scattering matrices for the system. But perhaps from a technological standpoint, the most interesting feature of the system was the fact that you could prepare different frequency superposition in your output state by controlling the modulation frequency of your Hamiltonian, or controlling the modulation that you're applying on the Hamiltonian. So as a very simple example, we looked at like a two-level system that we can modulate as a function of time. And by choosing the modulation properly, we could construct, for example, an equal superposition of photons at two different frequencies and suppress photons that are appearing at all the other frequencies. So this is a design that we could do very simply using the scattering matrix for these systems. And we could also demonstrate it experimentally that this works. So this was work done by Danielle, Alex, and Melissa from Yelena's group, who used silicon carbide color centers in order to implement this proposal for a modulated quantum system. They actually observed exactly what we expected, that you have this equal superposition of two photons coming out. So this is how you could, in fact, engineer the spectral content of these wave packets as well. And you can describe that again within the framework of these scattering models. Okay, so finally, let me go on to the last example that was related more to memory and not really to non-classical light storage. And here we were essentially looking at these non-Markovian waveguide QED systems. So systems in which you have these two-level system coupled to the bath. And for example, you can introduce a time delay, and the presence of this time delay and feedback would make the system effectively non-Markovian in nature. One of the interesting things that happens in these non-Markovian systems, and these non-Markovian systems are actually very interesting from a quantum information standpoint, but one of the interesting and simple things that happen is that you have what are called these long-lived light matter entangled states, which are called bound states. And these states are essentially eigenstates of the Hamiltonian for the system that can exist in principle if you don't have any other losses in your system indefinitely. But of course, in practice, you have absorption losses or you have some transmission losses in your mirror, and that is going to limit the lifetime of the system. But the lifetime of the system is going to be much much larger than the lifetime of the two-level atom. So you could perform information processing tasks on two-level atoms much faster than the leakage of this bound state. So this opens up the possibility of using these bound states for storing quantum information, because they are these long-lived light matter states. Now, when you're storing any kind of quantum information, one question that you would ask is, can I excite these bound states, and how efficiently can I excite these bound states? So when we think about excitation of these bound states, what you could show was that if you take single photons and you shine single photons and you shine single photons on this system, then the photons will almost completely be reflected from this non-Markovian system. So photons cannot, in fact, excite the bound state. And this just comes also from the fact that the scattering states of your Hamiltonian and the bound states of your Hamiltonian are orthogonal to each other. So you can't really excite a bound state with just a scattering state, but you could excite these bound states with two photon wave packets or higher number of photon wave packets, because the emitter could have a nonlinearity that would mediate interaction between these photons and then therefore excite and therefore you would have a finite probability of trapping one photon in the bound state and the other photon is going to be reflected back. And this is again something that we can observe using our scattering theory formalism. We actually calculate the scattering probability for this process. It turns out to be a non-zero probability for most of your input photon wave packets. And then you could ask the question of, what is the optimal photon wave packet to excite this bound state, right? Can we rigorously derive the photon wave packet that would excite this bound state with the maximum trapping probability, because that would be the photon wave packet that you would use for reading in and reading out from this quantum memory. And the answer was yes. So if we set up the scattering theory for this system, which we could do using our framework, we could in fact very rigorously calculate upper bounds on this trapping probability. And we could also provide photon wave packets that would reach this upper bound. And we showed that in the regime where the delay between the two-level atom and this mirror was large, you could actually have almost unity trapping probability. So you could use it with use it as a highly efficient read-in and read-out protocol for these quantum memories. And moreover, you could also excite larger pieces of quantum information. You could store larger pieces of quantum information in the system. So the size of your memory is now only limited by the number of bound states that you can set up. And if you take multiple emitters, instead of just thinking about one emitter, you can think about 2, 3, 10, or 100 emitters, and you can expand the size of your quantum memory. And you can store different superposition of these bound states in order to store different pieces of quantum information. And again, using the scattering theory framework, we could in fact design photon wave packets that could excite various superposition of these bound states. So we could map the quantum information that is present in these two photon state into quantum information that is stored in these bound states. So here is just a simple example of showing how you can excite the first bound state, second bound state, or an equal superposition of these two bound states by appropriately designing the two photon wave packet. Okay, so this brings me to the end of the second part of my talk, where I discussed these few experimentally interesting physics quantum systems. And now let me very quickly, because I realize I'm running a little bit out of time, go through the last part of my talk, which is design. And so the main idea here is actually very, very simple. And the idea is that if you have these simulation models that you can tractably compute and that are also differentiable, which is the case in most of our systems, then you can use these simulation models to automate away the design of a lot of devices. And the motivation here for a number of you who might have seen these results in a completely different context comes from this nanophotonics inverse design, where you're dealing with classical electromagnetic devices, not really quantum devices, but you could accurately simulate the physics of these classical electromagnetic devices using Maxwell's equations, and you could develop extremely fast and efficient software that could perform these simulations. So if you can then differentiate through this electromagnetic simulator, then you can use an off-the-shelf optimizer in order to design very robust and very compact electromagnetic devices, which look very different from how you would expect an electromagnetic device to perform a particular function would be. And we now have a very similar ingredient, which is a simulation model in the space of quantum devices. So then we could think about, can we improve the efficiencies of these quantum devices by using these automated design techniques? And so the idea here was that if you take your quantum system, which has some Hamiltonian as a function of time, and you can then simulate the scattering from this quantum system, and then you can design what kind of Hamiltonian should I have as a function of time in order to achieve a particular task. So in order to emit, for example, a particular state or have a particular transmission, etc. So then this would then allow us to automate away the design of these modulating signals that I'm applying on my Hamiltonian and come up with maybe counterintuitive modulation signal designs that we can still use in order to achieve high fidelity operations here. So, so we kind of thought about several problems that we can apply this general hardware design framework to. And so one of the things that we thought about were these transduction systems. So this was work that we've done in collaboration with Satvik from Yelena's group. And these transduction systems are essentially systems that convert photons at frequencies, at microwave frequencies, to optical frequencies. And the motivation behind using these systems is that if you want to communicate between, let's say, two superconducting quantum computers that are working at microwave frequencies, but they're separated by large distances, then you want to use an optical fiber in order to do this communication. So you need to convert your RF photon into an optical photon. And then you need this device that is a transducer in order to be able to do that. And one of the technologies that people often use to make these transducers is to make them with these solid state emitters, like rare earth ion emitters or color centers. And these emitters are essentially quantum systems that couple to both the microwave frequencies and the optical frequencies. So by driving these emitters appropriately, you can transduce from microwave to optical frequencies. However, one of the problems that happens and using these solid state systems is that all of the emitters have slightly different frequencies. So there is this inhomogeneous broadening that happens because not all the emitters, because of your fabrication process or the way you implanted these emitters, that the emitters can have different resonant frequencies. And this negatively impacts the efficiency, the transduction efficiencies of these quantum systems. So one of the questions that we really had was that can we use some simple pulse design in order to compensate for these transduction efficiencies, in order to compensate for this negative impact of inhomogeneous broadening on these transduction efficiencies? So could we drive it with a laser pulse and still achieve the performance that we could get from an ensemble with no or lower inhomogeneous broadening? And the result that we really got here was that yes, we could actually achieve order of magnitude improvement in the transduction efficiencies by simply modulating the laser pulse. And the forms of the laser pulse modulation that we get were, of course, somewhat counterintuitive. They were these laser pulses that we had calculated by these automated techniques. So there wasn't really much interpretation that we have currently been able to attach to it. But it definitely shows that these automation of hardware design can allow you to solve these more complex practical problems and achieve high fidelity operations with them. A very similar idea can be applied to these multi-emitter cavity QED problems, so which I introduced long back, where you have multiple emitters coupling to a cavity, and there we work mostly with these emitters that are identical to each other. Now, however, again, just as in the case of transduction systems, when we practically set up these multi-emitter systems, these emitters can have slightly different resonant frequencies, and because of these different resonant frequencies, you negatively start impacting any kind of cooperative effects that can happen in between these multiple emitters. So for instance, if you look at a system which has 3 emitters, but the emitter frequencies are very, very different and are inhomogeneously broadened, and you look at the transmission spectra of these emitters, you essentially find that you see peaks corresponding to the individual transmission spectras of the emitter in your transmission. And that really tells you is that these emitters are really acting as if they are independent and not really coupling to each other or coupling to the cavity mode. But then we could ask ourselves, can we apply a modulation signal, change the frequencies of these emitters as a function of time in order to compensate for this inhomogeneous broadening? So here what we did was that we tried to calculate a modulation that if applied on all of these emitters together, so we were assuming that we can only apply one potential on all of these emitters and therefore modulate the frequencies together, then can we mediate strong interactions between the emitters and the cavity mode? And the answer turns out to be yes. So we could actually calculate these modulation waveforms that could allow that when applied on this multi-emitter cavity QED system showed us transmission spectra which indicated strong collective response. So you see these hybridized polaritonic modes that you often see in these strongly coupled systems with multiple emitters, and that was just appearing because we were modulating the emitter frequencies properly. And then finally, we could also think about designing photon emission. So not only reducing the impact of inhomogeneous broadening in these varieties of applications, but also to design photon emission from these quantum systems. And the idea here was that, well, if you take this two-level system, as I discussed a few slides back, you drive it with a laser pulse. If you choose your laser pulse properly, you could emit multiple photons in your waveguides. You could, for example, emit a two-photon state. Now, if you don't do anything to the two-level system, the two-photon state that is being emitted is really a constant. It doesn't really depend. You can't really control it significantly. It is almost completely determined by the lifetime of your two-level atom. But then you could imagine applying a modulation on this two-level system and engineering the two-photon wave packet that is coming out of it. So we could actually cast this engineering problem in the language of matrix product states, but those are all details that we soon hope to put out as a paper. But the idea there was really that you could design different kinds of entanglement structures in your two-photon wave packets. So for instance, one important resource that people often use in quantum communication are these unentangled two-photon wave packets, so where you have two photons that are coming together. So the presence of one photon heralds the presence of the other photons, and they are in completely different frequency bands. And so by changing this modulation frequency as a function of time, we could in fact design a modulation that would allow us to put one photon at one frequency and then the other photon as the other frequency. And then you could, through some linear optics, separate those two photons in two different channels. And you can use that for heralding, for heralded photon sources, or as building blocks for larger, more complicated cluster states or entangled state protocols. So with this, I come to the end of my talk, end of my defense. So thank you all for listening.